There we go. Coming to you live from A210, the classroom here in Canelan High School. Couldn't see if I was rolling or not. And I almost crooked my neck just trying to look at it. Anyway, this is your last day of notes. We finished the book today. Congratulations, you have survived. Well, give it a minute or two. We'll see what happens. This is about the power law models. Yesterday was about an exponential model. This is about the power law model. So let's talk about the models. There is a linear model to express scatter plots and data. That's what I mean. I'm putting an equation to try and describe the relationship we see in the scatter plot. That's what I mean by a model. The linear model has the form y equals a plus bx. The exponential model has a form that goes y equals a times b to the x. And then the power law model, which we're going to focus on today, the power law model has the form y equals a times x to the n. You see the difference? Exponential function has x as an exponent. Power law has x as a base, like x to the 7 halves, or just x squared, like a parabola. Now, exponential models, as we saw yesterday, they become linear when we apply a logarithmic transformation to the response variable. Right? So that basically, to get our linear model, we would see L1, and then we would see the log of L2. Yeah. But power law models have a different story. They become linear when we apply the logarithmic transformation to both variables. So what am I talking about here? I'm talking about getting a linear looking scatter plot from curved data by having the log of L1 and the log of L2. See what I mean? That's different. Okay, here's why. Power law, y equals a times x to the n. I'm going to use a little trick from Algebra 2 logarithms here. So I'm going to go the log of y is equal to a times the log of x to the n. If I take the log of both variables, I'm taking the log of every single x value and the log of every single y value that I have in my scatter plot. So that's where the two logs would go, is right up against the variables. We take the log of the variable. Now here is a property of logarithms that you might not remember. If you have the log raised to an exponent, you're allowed to bring the exponent down and multiply. So that would be the log of y is equal to a times n times the log of x. Right? Well, this is a linear form. Look, it's like y equals a times x. That's a linear form. So let me write it one more time. A linear form. Can't get it wrong. Yep, let's go to page 2. And this will look familiar to what we did on day 1. Similar kind of notes. Let's see, well, I got to turn page on my other one. That doesn't make sense. Okay, the first thing we should do if we, see, now that's just lazy right there. Power law. I'll fix that before I post yours. To determine, or to get moving, the first thing you should do is determine that the scatter plot fits a power law model. Now there's things you could do with the y values, but they got to be arranged in a certain order. So basically, we're going to receive a nice hint in this chapter. Number 2, we're going to define L3 to be the log of L1, and then we're going to introduce L4 as the log of L2. We're going to take the log of both variables. View a new scatter plot with L3 and L4. And then, of course, we'll evaluate linearness like we did yesterday. You can, that's the visual on your scatter plot, or you can look at the correlation or a residual plot or R squared. Then you're going to create a least squares regression line, and this is how you do it. You hit the stat button. You go over to the calc part. You do a number 8 for L3 and L4. This line will be of the form log of y hat is equal to a plus b times the log of x. Number 7, know that this line does not predict y hat values. It predicts log of y hat values for log of x values that you put in there. Well, that's not really helpful yet. We've got to rewrite our equation to make it helpful. However, you could create a residual plot in order to make sure that you further examine your linearness in case you didn't a minute ago. You could do it on your calculator, but you'll be given one of these. There's no reason for us to go through it. It's not very fun to do. Then number 9, you can get a prediction for y hat after you will alter your least squares regression of the log of y hat is equal to a plus b times the log of x. All right, by doing this math to both sides of the equation, you do this. You go 10 to the log of y hat. It's the same math we did yesterday. And then we go 10 to the a plus b log of x. Now, because this log is up here that wasn't there yesterday, that's going to change our rules here a little bit. So I'm going to go down here, and I'm going to go 10 to the log of y hat is equal to, I'm going to make this two different bases, 10 to the a times 10 to the b log x. Okay, now here I'm going to use this property of logarithms again. That b can go up there above that x. Yeah? So this would be y hat is equal to 10 to the a times 10 to the log of x to the b. And you guys, this 10 and this log cancel. Those are inverse operations right there. So I get y hat is equal to 10 to the a times x to the b. There it is. The x is no longer an exponent like it was yesterday. This is power law form. All right. Plot the original scatter plot along with the new power law equation. I'll just put EQ right there for y hat. Then predict anything you want, unless, of course, you go about predicting extrapolation and you're just being silly. I almost called you stupid, but you didn't do it, so it just didn't seem appropriate. Number 12, you could do some inference, like, for example, a confidence interval on the slope, or, you know, that kind of thing. For the slope of your least squares regression line, that's that one back up there, right? Of course, we're not going to do that either, though. We're just going to make some predictions and call it a semester. You know what I mean? Notice that the sloppy from your least squares regression line, let's go back to the least squares regression line and look at the slope. There it is, b, ends up becoming the exponent. That slope ends up becoming the exponent. The power law has a power, and the power that you get that describes whatever shape you have is the slope of the original least squares regression line after you took the log of x and y. Now, do not turn the page unless you are prepared emotionally to be on your last page of notes for AP Statistics. I'm trying not to cry, guys. I'm trying. This is it. This is our last moments with all of these videos and all of this damn pandemic and AP Statistics. This is the end of our video life together. Let's go to a book example, shall we? Hopefully there is a picture of an ugly person. I'm gonna get myself a Libro and go to page 800. And sadly, it's a fish. In the preceding example, we already looked at this example once, but we're going to take a different approach to it. In the preceding examples, we used powers and we used roots to find a model for predicting the weight of the Atlantic Ocean rockfish from its length. Coolest name for a fish, really. We still expect a power model of the form weight equals a times length to the third. What we did the other day was, like, since we think this is x to the third to get here, like, would we take a cube root of this or something like that? It's on the other page. Let me find the rockfish. Rockfish, where's my rockfish? Lost it. Oh, it's over here. Yeah, we cubed the length so that it would match up with the width, okay? But this time we're going to use the logarithmic transformation. So we take the logarithm of both variables, because that's what we just learned on the last page happens, and look what you have here. The log of the length and the log of the width, if it's a power law model, becomes perfectly linear. That's pretty badass. R squared, 99.9, that's a smoking hot R squared right there. That says we got a pretty straight line. There's your residual plot. Based on the output, explain why it would be reasonable to use a power law model to describe the relationship. You guys could be asked this kind of question on your test. Why is it reasonable to use a power law? Well, the answer is because I took the log of both variables and it straightened the hell out of this scatter plot. That's why. When I take the log of both variables, that suggests power law. Part B, give an equation for the least squares regression line. Okay, that would be y hat equals negative 1.8999940 plus 3.04942 x. But I should put some logs there. So look what they did. They went log of y hat, and then it's equal to this, and they put log right where the x is. Not in front of the, not the whole log of both sides of the equation. They put the log right where the y is and right where the x is. Okay, and then they say, suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. How are we going to find its weight? Well, you go to put 36 centimeters in here, and what happens is you got to take the log of 36, multiply it by 3.04942, and then subtract 1.8999940, and you get 702.1 grams. All right, log of both sides straightens out your data. So here we go. We're going to do a Larson example. I picked some data of, I don't know when I did this a couple of years ago, but here's what I want you to do. I'm going to pause the video. I want you to put list 1 and list 2, and let's take a look at some data. Do that now.